Hello. Okay, so hello everyone. This is lecture number 2 on units and measurements. So in the previous lecture, we started with the discussion on your measurement of length, how the lengths are being measured. Today we will go on with the final concluding portion of that measurement of length, and then we can go to measurement of time and move on with the further discussions. Okay, so I'm Samir Lawankar. Let's begin our discussion. Okay, so right now we are on the third portion, that is measurement of length. Before this, we have already covered with the introduction part and the international system of unit, that is SI unit. In the introduction portion, we basically understood why was there a need to what were basically the base units and fundamental units and derived units. Then various different units are being understood in the international system of units. Why was there a need to convert SI units, etc. were being dealt with here. And finally, in the third portion, in the previous lecture, we concluded the study by understanding both the measurement of large distances, very large distances, and measurement of very small distances. So in the measurement of large distances, we understood the concept of parallax method. For the measurement of small distances, majorly the microscopes are being used. The tunneling microscopy is being used in recent times. And one of the example of how we used concentrations to derive the final value of the distance was being analyzed. One of the example was being used for the oleic acid. So let's complete the discussion for the measurement of length, and then we can move on to the fourth point, that is measurement of mass. Okay, let's move on. Okay, so range of length. So what are the ranges of lengths to be which we just need to understand? Small portion only. Okay, so let me start. Okay, so range of lengths. So the sizes of the objects we come across in the universe vary over a very wide range. Quite evident. Even if I take anything which is point blank at my in my mind is one we can say as a person, or let's say one is your planet. Then one thing can be, let's say, watch, right? If I take these three examples only, person is in terms of some meters. Like let's say we can use some meters to find out the distance or the height of the person. A planet, a distance of the planet, even diameter of the planet are basically in kilometers, right? And a watch is let's say some centimeters. You can calculate it, right? So you can say that ranges of lengths are very, very different for many things. Like if I take a molecule, and for molecule it is very small, it's in the order of 10 to the power minus 10 meters, etc. Right? So that thing is being dealt here. Okay, so the sizes of the objects you come across in the universe vary over a very wide range, quite evident. These may vary from the size of the order of 10 to the power minus 14 meters of the tiny nucleus of an atom to the size of the order of 10 to the power 26 meters of the extent of the observable universe. So these are the ranges of the distances, length, etc. Anything which you may prefer, you can speak up to this. Table gives the range and order of lengths and sizes of some of these objects. Okay, so just refer to the table here. Don't mug up anything from here. This is just for your information reference purposes only. So as you can see here, the size of proton is 10 to the power minus 15 meters. Here it is 10 to the power minus 15 meters. Then atomic nucleus 10 to the power minus 14 meter, and this goes on to increasing portion with the highest for distance to the boundary of the observable universe will be 10 to the power it's 26 meters. Okay, so just it's for reference purpose that there can be ranges of lengths. Okay, we also use certain special lengths units for short and large lengths. So now understanding every concept in terms of meters is a little tedious. Every time we cannot write, let's say 4.69, let's say 098 into 10 to the power minus 10 meters. Writing these all terms again and again and again will take up much time, and it is very quite confusing also. Therefore what we do is we just directly use some concept like Armstrongs, or let's say Fermi, or let's say kilometers, etc. And then directly utilize this in our works. Okay, so next thing is, so what are the spatial lengths? So first is like, let's say Fermi. So what is Fermi? One Fermi is equal to 1f divided by small f. 1f is equal to 10 to the power minus 15 meters. Okay. Next thing is 1 angstrom. 1 angstrom is which is equal to 10 to the power minus 10 meters. Okay, please remember angstrom because this will be utilized majorly in your chemistry portions. Okay. Next thing is one astronomical unit. What is one astronomical unit? One astronomical unit is equal to 1 AU. It is noted by AU, which is average distance of the sun from the earth, which is equal to 1.496 into 10 to the power 11 meters. Next thing is one light year. You may have heard of light years quite evident in your surroundings. So generally for astronomical portions or for finding out the distances between the celestial objects, we use the distance in terms of light years. So what is one light year? One light year is basically 9.46 into 10 to the power 15 meters. The definition is also given to you on the screen. The definition of one light year is basically the distance that light travels with a velocity of 3 into 10 to the power 8 meter per second in 1 year. So basically, if you multiply the value of 3 into 10 to the power 8 meter per second into what we can say 365 into 86400, because there are in 1 day there is 86,400 seconds. Then in 365 days, 86,400 into 365 multiplied by 3 into 10 to the power 8 meter per second, you will get the answer as 1 light year. Whatever I spoke, I'm just writing it so that it will be much clearer. So this value is just calculated as equal to 3 into 10 to the power 8 into 86,400 seconds for 1 day, and because an year contains 365 days, so basically this. So when you just calculate, you will get answer as equal to 9.46 and 10 to the power 15 meters. Okay, some light changes might be there because sometimes it is taken as 366. The value of light is also not exactly 3 to 10 to the power 8, something 2.99. So some sort of difference would be there, but approximately it would lie, or it can be said as equal to 9.46 and 10 to the power 15 meters. So this is general consideration that one light year is equal to 9.46 into 10 to the power 15 meters. Okay. Next thing is one parsec, which is equal to 3.08 into 10 to the power 16 meters. Parsec is the distance at which the average radius of the Earth's orbit subtends an angle of 1 arcsecond. So this is the information provided here. Fine. So that is the ranges of length which I needed to cover. Now so this was just for reference portion, that yes, but just think with the concluding part is that you should just remember what is one Fermi, what is one Armstrong's, what is one astronomical unit, what is one light year, and what is one parsec. Just these are some of the things which you need to remember. Okay, fine. Let's move on then. Let's move to the next discussion now, that is measurement of mass. So how is mass being calculated? Okay. So please listen to it carefully. So mass is a basic property of matter. It does not depend on the temperature, pressure, or location of the object in space. Right? So just to explain again, so if let's 0 kelvins, or let's say the temperature is 273 kelvins. Let's say the pressure is 0 Pascal, or let's say the pressure is 273 Pascals. I'm just taking vague numbers, just don't refer to this at anything. Let us say the location is Earth, or let us say the location is Moon. At each and every location, at any permutation combination, at everything, at every concept, if you take anything from temperature, anything from pressure, anything from location, the value of mass will always be same. Mass will be same. Okay, fine. So this thing is explained, this thing is explained. The SI unit of mass is kilogram. Please remember this, quite evident, it's easy to understand. It is general terms only. So the SI unit of mass is kilograms, kg. The prototypes of the International Standard Kilogram supplied by the International Bureau of Weights and Measures, that is BIPM, are available in many other laboratories in different countries. In our country, it's in Delhi. So it's in India, this is available at the National Physical Laboratory, NPL, New Delhi. This is just theoretical version, as in how to quantify kilogram. What is the prototype for International Standard Kilogram? Okay. While dealing with atoms and molecules, the kilogram is an inconvenient unit. Quite evident, because the weight of atoms and molecules will be much smaller than kilogram. Right. So in that portion, what we use an atomic mass unit. So in this case, there's an important standard unit of mass called the Unified Atomic Mass Unit. Please, this is very important concept of atomic mass unit. Please be very careful while understanding this. So in this case, there's an important standard unit of mass called the Unified Atomic Mass Unit, also denoted by small u, which has been established for expressing the mass of atoms as, how we specify them? We specify it as one unified atomic mass unit is equal to 1 U, which is equal to 1/12 of the mass of an atom of carbon 12 isotope, including the mass of electrons, which is equal to 1.66 into 10 to the power minus 27 kgs. Okay. So the above portion which is written 1/12 of the mass of an atom of a carbon 12 isotope, including the mass of electron, is just definition that is being conveyed about unified atomic mass unit, and the value for 1 U is basically referred as or basically equal to 1.66 into 10 to the power minus 27 kgs. Okay. Next thing is mass of commonly available objects can be determined by a common balance like the one used in a grocery shop. So you may have seen such things which we are used basically in vegetable shops or let's say in grocery shops. So these balances can be used for the calculation of your weights, right? Large masses in the universe like planets, stars, etc., based on Newton's law of gravitation, can be measured by using gravitational method. Okay, so large masses can be found out using gravitational methods, and small, generally commonly available objects can be measured using this common balance. Okay. For measurement of small masses of atomic like subatomic particles, etc., we make use of mass spectrograph. Okay, so we won't go into much detail of what is mass spectrograph. So you can just remember this, that for what is being used for large masses, what is used for small masses, what is used for generally available objects. Okay, so we make use of mass spectrograph in which radius of the trajectory is proportional to the mass of the charged particle moving in a uniform electric and magnetic field. Okay, so that is just the principle of how mass spectrograph works has been explained. Right? Let's move on. Okay, so range of masses. So basically, as we understood the concept of range of electrons, similarly we are understanding the range of masses. So electron, it can go varying from 10 to the power minus 30 kg to observable units which is 10 to the power 55 kg. That is how, what is the range of your complete mass. Okay, so the masses of the object we come across in the universe vary over a very wide range, quite evident. These may vary from tiny mass of the order of 10 to the power minus 30 kg of an electron to the huge mass of about 10 to the power 55 kg of the universe. Table gives the range and order of the typical mass of various objects. Okay, so again the table is just for reference. You don't need to mug up anything. This is just to explain what is the variation of the mass or the range of masses available in the entire universe. Okay. Let's go on to the next discussion, that is measurement of time. Okay. So what will be understanding measurement of time? Let us see. Okay. Let's start with the range of mass. This is not, so just ignore this line. This is not for range of masses. Okay, so to measure any time interval, we need a clock. Quite evident, we need a clock. We now use an atomic standard of time, which is based on the periodic vibrations produced in a cesium atom. Okay, so how is this basically? What is this 1 second? What is this 1 second? What is that? Let's say I cite it here. Why only, let's say, this amount of duration of t is called as 1 second? What is this 1 second? The history of this has been explained. So we now use an atomic standard of time, which is based on the periodic vibrations produced in a cesium atom. Right, recently, this atomic standard of time is based upon the periodic vibration produced in cesium atom. This is the basis of cesium clock. So there are different types of clocks available, like cesium clock, quartz clock, etc. One of the bases been explained here, that is cesium clock. So this is the basis of the cesium clock, sometimes called as atomic clock, used in the national standards. Okay, that is the most accurate, I guess, which is being available. Such standards are available in many laboratories. In the cesium atomic clock, the second is taken. Now, please refer to this line very, very carefully. So, in the cesium atomic clock, a second is taken as the time needed for 91192631770 vibrations of the radiations corresponding to the transition between the two hyperfine levels of the ground state of cesium-133 atom. All in all, just to explain to you in a very easy statement, there are periodic vibrations happening due to the cesium due to the radiation in the cesium, and due to which we are finding out the complete time duration. Okay, so again for your reference only, the vibration of the cesium atom regulates it would be much preferable if we remember this thing, because this is very useful, this line. Okay. Let's move on. The vibrations of the cesium atom regulate the rate of the cesium atomic clock, just as the vibrations of a balance wheel regulate an ordinary wristwatch, or the vibration of a small quartz crystal regulate a quartz crystal. So they are just trying to explain you as there are different types of clocks. So cesium clock works on cesium atom similarly as the quartz crystal, quartz watch works on quartz crystal, and the balance wheel regulate an ordinary wristwatch. So they are just explaining those concepts here. The cesium atomic clocks are very accurate. So I think right now the most accurate clocks are cesium atomic clocks only. Okay. In principle, they provide portable standard. The national standard of time interval second as well as the frequency is maintained through 4 cesium atomic clocks. So basically, this national standard is being maintained through 4 cesium atomic clocks. Okay. Let's move on. So next thing is your cesium atomic clock is used at the National Physical Laboratory again, where we understood the concept of where the national standard for mass is also being kept. So a cesium atomic clock is used at the National Physical Laboratory (NPL) New Delhi to maintain the Indian standard of time. In our country, the NPL has the responsibility of maintenance and improvement of physical standards, including that of time, frequency, etc. Note that Indian Standard Time, that is IST, is linked to this set of atomic clocks only. So you may have heard that we have a increase of 630 hours or 530 hours approximately from the Greenwich time, right? That is basically your IST. So that IST is being linked to these atomic clocks only. Okay, this atomic clock is cesium clocks. Okay, the efficient cesium atomic clocks are so accurate that they impart the uncertainty in time realization as plus minus 1 and 10 to the minus 13. So you can understand the accuracy of this. So you can see the accuracy of this. So IST is basically Greenwich time, Greenwich Meridian time plus 5 hours 30 minutes, right? And after that also now when we are trying to find out the efficiency, so that was regarding this we can understand just the accuracy, that is in 10 after 10 to the power 13 second. Okay, so explanation is given in the next line only. So this implies that the uncertainty gained over time by such a device is less than 1 part in 10 to the power 13. That means they lose or gain no more than 3 microseconds in 1 year. So that is the accuracy of this atomic clocks. This is very good atomic clock. These are having very good efficiencies. Okay, more accuracy is being imparted here. In view of the tremendous accuracy in time measurement, the SI unit of length has been expressed in terms of the path length traveled in certain intervals of time. So basically that is 1 upon this is basically 320 power 8 meter per second approximately. That is the speed of light. Okay, so 1 upon 299,792,458 of a second. The time interval of events that we come across in the universe vary over a very wide range. Okay, the time interval of events that we come across in the universe vary over a very wide range. Quite evident because sometimes if we are taking out billion years, when were the dinosaurs being born? So that is very dated back. And let us say any recent happening is being done in the morning, so the amount of hours are very less. Or let's say when I started this lecture, it's just 15 minutes only or 20 minutes only. Again, range of timings are very different depending upon what is the point of reference. Okay. Next thing is again, this is not range of masses. This is basically range of time only here. Okay, so table gives a range and order of some typical time intervals. As you can see, this is a typical ranges given to you. So note that the ratio of the longest and the shortest length of objects in our universe is 10 to the 41. As you can see, age of the universe is this and minus 24 is this. So if I do a ratio of them, you will get that there is a difference of 10 to the power 41. About the ratio is about 10 to the power 41. Okay. So lifespan of most unstable particles 10 to the power minus 24 seconds, and the age of the universe is 10 to the power 17 seconds. Okay. Interestingly enough, the ratio of the longest and the shortest time intervals associated with the events and objects in our universe is also about 10 to the power 41. This number 10 to the power 41 comes up again in previous table, which lists typical masses of object. The ratio of the largest and the smallest mass of the object in our universe is about 10 to the power 41 squared. Is a curious coincidence between these items are purely accidental. So these all things are just explaining, just increasing your curiosity towards understanding the chapter. So they are just saying that if you do the ratio of this and this, It is coming 10 to the power 41. Similarly, if you do the ratios for the masses also, then also for the highest and the lowest thing, it is again coming to the 41 only. So the ranges, how are they coming coincidence is just to explain or just to understand how brilliantly our complete surroundings is being captured or being made. Okay, fine. Let's move on. Okay, so now it's a typical topic starting regarding accuracy, precision of instruments and errors in measurement. Okay, so please be careful, please understand this very carefully. Not a very typical subject, but because of different concepts coming in, this may be a quite tricky, but if you pay attention, this will be very, very easy. Okay, fine. So let's start with definitions and then we move on to different results or different explanations being explained in the subsequent slides. Okay, so measurement is the foundation of all experimental science and technology. Okay. The result of every measurement by any measuring instrument contains some uncertainty. So this is the quite certain, right? So these, I think explanation is being done. So first, let's say I explain also. Let's say this is a meter scale, right? This is a meter scale, and there, let's say these are the divisions being explained. Okay, wait. That will make it much more clearer. Fine. So let us say we need to measure something from this portion to this portion, right? But sometimes what we do is, let's say this line is not been coinciding with this, we approximately take it to be equal to this, right? So that is also some part of uncertainty only. Sometimes what happens is, because there is some thickness of these projection, these spokes being made up here, right? These spokes also take us some area. So now maybe the distance would have occurred only till this portion. It won't have occurred till this portion. Then there is this uncertainty also arising. There are many such uncertainties. Sometimes there is an error in the instrument only. The amount of what we can say. Let us say, so what happens in a screw gauge, the distance is being measured depending upon the circumferential movement of the screw gauge, right? We know the least count of this. We know that, okay, after one circle, let's say X amount of distance is being covered. But what if this X distance is not existed? This is some X minus, let's say 0.1 meters, or let's say 0.1 into 10 to the power minus 3 meters, let us say. So that is the uncertainty coming into this portion here. That is the basic crux or basic idea of why we are studying this as an error concept. Okay, so let's start understanding this here. So this thing is done, this thing is done. Okay, so this uncertainty is basically called as error. Okay, so this uncertainty is called as error. Every calculated quantity which is based on measured value also has an error. Quite evident, everything which you try to calculate, severe measured value will also have an error. We shall distinguish between two terms, accuracy and precision. So you need to understand these two terms very carefully. Don't make a mistake of understanding these two things as same thing only. Both things are different. Okay. Even after explanation, if you cannot understand, I will try to use some diagrams also to make you understand much more clearly. For now, let's understand everything which is written. Okay. So let us understand this. What is basically the difference between your accuracy and precision? So the accuracy of a measurement is a measure of how close the measured value is to the true value of the quantity. Okay. Example, let's say the true value, let's say I write TV as the true value. The true value of the quantity is 5.35 kgs. Okay. If I get the measured value as equal to, let's say I do 3 tests. One value is we got 5.3 kgs. One I got 5.32 kg. One I got 5.34 kg. Right. So the accuracy of a measurement is a measure of, okay. And another thing, again I did 3 experiments. I got the answer as equal to 5 kg, 5. Let's say 6 kg, and let's say 5.9 kg. Right. So as you can see, the first set of results and the second set of results, the first set of results are much more closer to the real value. So we can say that here the accuracy is much higher. Accuracy is much higher. Here the accuracy is low. That is the explanation. Okay, that is only been explained here. So the accuracy of a measurement is the measure of how close the measured value is to the true value of the quantity. Okay. Precision tells us to what resolution or limit the quantity is measured. Okay, so precision example can be explained also. So let us say again. Let's say the true value was 5.35 kgs only, right? Next thing is, let's say I did again two tests. This is first test, this is second test. My first test was, let's say, 4.9 kg. Let's say 4.9 or let's say 4.8 kg, and let's say 5 kg. My another test was, let's say, 5 kg, 5.5 kg, and let's say 5.3 kg. It is quite evident that the results of the second test are much near between 5.35 kg, right? But you can see the variation is very, very high here. The variation is very, very much less here. It is just 0.1. Here it's 0.5, 0.3. The variation is much higher. Then we can say that the precision is high here, because okay, we are getting wrong answers, but actually the precision is always right. Maybe there is some error we are trying to make when you're trying to calculate this measured value. If we just add that error, then or add the correction value, then we can get the results which are being very, very close to the true value. Okay, so here precision is high, here precision is low. Okay, fine. So let's move on then. So this thing has been explained. So precision tells us to what resolution or limit the quantity is measured. The accuracy in measurement may depend on several factors, including the limit or the resolution of the measuring instrument. Okay, so yes, the instrument also plays a very crucial role on calculating or finding the accuracy and the precision of the measurement. That's how the instrumental error thing came into picture. We will try to understand the concept of instrumental error in subsequent slides, I think. For now, just understand this gas key, because there can be errors, there can be faults in the instruments also, and due to that there can be there are chances that the accuracy of the instrument can be reduced. Okay. So for example, suppose the true value of a certain length is near 3.678 meters. So now let us try to understand this example clearly. I will keep on writing also on the left, so that 2 times revision would be done. Okay, so let us say that true value is given. Okay, so let me write. The true value is given as 3.678 meters. Okay. In one experiment, using a measuring instrument of resolution 0.1 centimeter. What does it mean by measuring instrument of resolution 0.1 centimeter? The maximum value which it can be said, which the instrument can deliver correctly, is just till the first decimal place. Okay, so the answers can be only in the range of, let's say, 3.3, 3.4, 3.5, 3.6, like this. It cannot be 3.52. This answer cannot be we cannot get using the measuring instrument of resolution 0.1 centimeter. Okay, so the measured value is found to be 3.5 centimeters. So when the experiment was being done, the value was found to be 3.5 centimeters. Sorry, 3.5. So this is centimeters only. Sorry, then it's my mistake. Okay. While in the another experiment using a measuring device of greater resolution, this time the resolution was 0.01 centimeter. Okay. So this time we got the answer as 3.38 centimeters. Okay. The first measurement has more accuracy. Why it has more accuracy? Because it is much more closer to the true value, but less precision. Why less precision? Because the resolution is only 0.1 centimeters. While the second instrument is less accurate. Why? Because it is much more far from the true value, and it is more precise. Why it is more precise? Because it has higher resolution. Okay. So that is one of the example in which you can what is the difference between accuracy and precision. Okay. One was the example which I conveyed regarding precision. Only precision thing varied. So regarding precision, one thing is that. Another thing is regarding this. So resolution also has an effect on the precision. Okay. Fine then. Let's move. Thus, every measurement is approximate due to errors in measurement. Okay. In general, the errors in measurement can be broadly classified as two. One is systematic error, one is random. Okay, so now let us try to understand these two topics. So let's start with the systematic errors. Okay, as the name suggests, systematic. So what can be understood by systematic? There is some system involved. There is some what we can say in if I take it as a very physical term, we can say that there is some engineering involved. These things can be understood, or this can be captured if we look at the pattern very carefully. Okay, if we look at the pattern, then we can just by observing the pattern we can find out a correction factor, and then if we try to reduce or increase whatever the sign convention of correction would be, we can find out the exact true value. Okay. Okay, then let's understand this thing now. So the systematic errors are those errors that tend to be in one direction. Okay, so they can be either positive or either negative. Some of the sources of your systematic errors are, the first source is your instrumental errors. Instrumental errors that arise from the error due to imperfect design or calibration of the measuring instrument. Imperfect design or imperfect calibration of the measuring instrument, zero error in the instrument. So what does it mean by zero error in the instrument? What really happens is, let us say there's a galvanometer. What is the usage of galvanometer? Galvanometer is basically used. So if I try to apply or try to use it in a circuit, if a current passes through the circuit, it shows a deflection. Okay. So let us say this is the galvanometer being used here. And let's say this is the tip of a galvanometer. Sometimes this tip won't be at zero. Sometimes this tip won't be at zero. Let's say this would be zero. So if it is not at zero, then actual value of the deflection cannot be occurred or cannot be visible. I can take this as an example for the compass also. Let's say the compass has to show north at some direction, but it is not showing north. There is some difference in the exact point which it should be showing. That is nothing but called as your zero error. So this zero error is not applicable, I think, for compass, but it can be applicable for things like let's say your galvanometer, etc. Okay, so I made you understand what is the basic crux behind what is this zero error. Okay, so let us understand this by an example. So for example, the temperature graduations of a thermometer may be inadequately calibrated. It may rate 104 degrees Celsius at the boiling point of water at STP, whereas it should be 100 degrees Celsius. So this is the error. So everybody knows that water boils at 100 degrees Celsius only. But if because of calibration error, or let's say any other effect, if it is showing 104 degrees Celsius, then it is quite clear that there is an instrumental error only, right? Similarly, again, another example can be in a vernier caliper. The zero mark of the vernier caliper may not consider the zero mark of the main scale. This is nothing but your zero error. Okay. Or simply an ordinary meter scale may be worn off at the end. So because of worn off, instrumental error can again occur. So basically, what does it try to understand? So let us say this is the complete meter scale, right? So if these things have been chipped apart here, there will be some error when we are trying to make, let's say, using this meter scale, we are trying to find out, let's say, 10 meter distance. The 10 meter distance may not be accurately 10 meters. This may be 9 point something or 10 point something, depending upon how we are measuring the data. The actual result would be much more higher or lower, depending on how we are understanding this. So instrumental errors can be either positive or either negative. Okay. Next thing is imperfection in experimental technical procedure. So what is this? To determine the temperature of a human body, a thermometer placed under the armpit will always give a temperature lower than the actual value of the body temperature. Quite evident because it's on the outer side. Other external conditions such as changes in temperature, humidity, wind velocity, etc. during the experiment may be systematically affecting the measurement. So they are just saying that the surrounding environment also leads to erroneous results. Okay. Fine. Next thing is personal error. So basically there are three types of considerations of your systematic errors. The first was regarding the instrumental error. The second was regarding the imperfections in the experimental technical procedure. And the third is regarding the personal error. Okay, so personal errors that arise due to an individual's bias, lack of proper setting of the apparatus, or individual's carelessness in taking observations without observing proper precautions, etc. In very easy terms, it is just because a person does some task. If a person does not do careful observations or careful tasks, then there may be errors. These are only called as personal errors. Let's say you need to find out or you need to measure something using a vernier caliper. You didn't actually. So one of the principle of vernier caliper is that the above line should measure the below line. So there's a vernier scale, there's a main scale. The we take the answer. One of the procedure in which we take the answer is that the graduations of the above line should measure the graduation of the below line. If let's say by our personal by our eyes we understood that the fifth graduation is same and not the ninth graduation, but actually it was a ninth graduation, then it's a personal error only, because here the vernier caliper was correct. The thing which was wrong or the thing which led to error was our own eyesight, or let's say our lack of carefulness. Okay, so this is basically the personal error. Okay, so personal error that arises due to individual's bias, lack of proper setting of the apparatus, or individual's carelessness in taking observations without observing proper precautions, etc. One of the example is also given. So the example states that, for example, if you by habit always hold your head a bit too far to the right while reading the position of a needle on the scale, you will introduce an error to parallax. Quite evident, we understood what is the basic concept of parallax in the previous lecture only. Okay, now this is an important point. Systematic errors Systematic errors can be minimized by improving experimental techniques, selecting better instruments. If a better instrument is being selected, then quite evident that there are higher chances that the accuracy is right. There is no zero error. है ना? Improving experimental techniques, we can do experiments much more clearly. Our experimental analysis should be done at let's say STP always, so that there won't be much error. And third is that if you do the calculations, the personal bias should be removed as far as possible. Either machinery should be used directly, or if it is used, if a personal has to be implied by anyhow, then the observation or the carefulness of that person should be at a very higher pace or at higher level. Okay. The systematic errors can be minimized by improving the experimental techniques, selecting better instruments, and removing the personal bias as far as possible. Okay, for a given setup, these errors may be estimated to a certain extent and the necessary correction may be applied to the readings. Okay, so if we find out that error, just apply the corrections and you will get the correct answer, the true way. Okay, for a given setup, these errors may be estimated for some given setups. This systematic errors can be found out. Basically, they can be estimated. This may be estimated to a certain extent and the necessary corrections may be applied to the readings. Okay, so this is how systematic errors are being explained. Let's move to the second part, that is your random errors. Okay, so what are random errors? As the name says, random. So they can be either positive, negative, and there is no certain pattern involved in random errors. Like there can be fluctuations happening. It can be either go to let's say 1 volts, or sometimes doing a particular agent won't even go to 0.1 volts. So this is basically random errors. Okay. So the random errors are those errors which occur irregularly and hence are random with respect to sign and sign. Okay. These can arise due to random and unpredictable fluctuations in experimental conditions. So these are the basic examples being explained about random errors. So how can they can arise? They can arise due to random and unpredictable fluctuations where in experimental conditions. For example, unpredictable fluctuations in temperature, voltage supply, mechanical vibrations of experimental setups, etc. Personal bias errors also by our taking reading. So let's say I took a reading. For one time I took my eye above, then due to parallax it may have looked down, and one time I looked it from below, then it may have looked up. So I am not taking the actual answer, I'm taking some random errors, and that error refers to the angle of inclination at which my eyesight is, right? Major thing is that it should always be normal to the reader, but it is not always the case. People do errors like this, so it has to be removed as far as possible. Okay. For example, when the same person repeats the same observation, it is very likely that he may get different readings every time. Maybe there are chances, even if you do the results, if you, when you will do laboratory experiments, you will get different observations. There are higher chances that you will also get different observations. Okay. Now, next thing comes to the least count error. So, what is the least count error? Let us try to understand, and then we can conclude. I think we can conclude this lecture today. So, least count error, the smallest value. I also explained what is least count in the previous lecture only. So, here is a complete definition, bookish definition here. The smallest value that can be measured by the measuring instrument is called its least count. Okay, quite easy definition. This is the only thing which I also explained. So, it's the smallest value that can be measured by the measuring instrument is called its least count. So all the readings or measured values are good only up to this value. The least count error is the error associated with the resolution of the instrument. What does it line try to depict? We will try to understand using the example given below. So please refer to the example, then you can understand the above line. So for example, a vernier caliper has the least count of 0.01 centimeter. A spherometer may have at least count of 0.001 centimeter. Okay. Least count error belongs to the category of random errors but with limited size. It occurs with both systematic and random errors. Okay, so first of all, let me try to explain the example. Let us say we are having something. So there is, let's say we are trying to capture the distance or the diameter of this ball. Using the vernier caliper, I got the answer as equal to 3.42 centimeters. Using a spherometer, I got the answer as equal to 3.419 or 0.418 centimeters. Let us say 418 centimeters, right? So, and the true value was 3.4179 centimeters. Let us say. So, it is quite evident that as you increase the resolution, there are higher chances that the amount of error is being reduced, right? If you do 3.42 minus 3.4179 and you do 3.418 minus 3.4179, the amount of error is less for spherometer than for vernier caliper, right? So as you keep on increasing the resolution, then the error decreases. Or we can say that as we keep on decreasing the resolution, the amount of error increases. So that is only one of the examples being explained. Okay, so least count error belongs to the category of random errors but with a limited size. It occurs with both systematic and random errors. Okay, if you use a meter scale of measurement for measurement of length, it may have graduations at 1 millimeter division scale, spacing or interval. So you can also refer to this. Just look at the scale. You can find that the smallest value which you can measure using a meter scale is 1 mm. Hence, the least count of this meter scale is 1 mm. Using instruments of higher precision, improving experimental techniques, etc., we can reduce the least count error. Quite evident, if you use higher precision, higher resolution would be possible, and there are higher chances that the accuracy is increased. Similarly, if you improve the experimental techniques also, you can reduce the least count error. Okay. Repeating the observation several times and taking the arithmetic mean of all the observations, the mean value will be very close to the true value of the measured quantity. So these are just techniques we are evolving. So we try to repeat the observations. If you have a very high sample size, then there is a very less probability that the amount measured value which you got is not true or not accurate enough. Okay. So repeating the several times, sometimes what happens is that there is a positive error, there is some negative error, these plus and minus gets cancelled and we get the true value. So repeating the observation several times and taking the arithmetic mean of all the observations, the mean value would be very close to the true value of measured. Okay, fine. So these are just things which can be understood directly by understanding or reading the lines only. Fine. Let's move to that is absolute error, relative error, and percentage error. Just try to understand very easy concepts. So let's try to complete it quickly. Okay. So suppose the values obtained in several measurements are A1, A2, A3, and so on till An. The arithmetic mean of these values is taken as the best possible value of the quantity under the given conditions of measurement. So what is the arithmetic mean? Arithmetic means just the summation of all these values divided by the number of values. In this case scenario, number of values equal to n. Or we can write it as A mean is also equal to summation I is from 1 to n ai by n. So this is just the notion of how we use. So it's ai by n. Here I can be 1 to n. So this is summation sign. So a1 plus a2 plus a3 and so on till an. Okay. So this is because, as explained earlier, it is reasonable to suppose that individual measurements are as likely to overestimate as to underestimate the true value of the quantity. Okay. So they are just trying to make you understand the advantage of using an AB value, which we understood in the previous point. Okay. The magnitude of the difference between the individual measurement and the true value of the quantity is called the absolute error of the measurement. Okay. So this is remember delta I. So this absolute error is nothing but equal to your AI minus A true. Okay. In absence of any other method of knowing true value, we consider arithmetic mean as the true value. Okay. So this true value is nothing but equal to A mean. Because we don't have the true value, this A mean can be used as your arithmetic mean. So then the errors in the individual measurements from true values will be nothing but delta A1 is equal to your A1 minus A mean, and similarly delta A2 will also be equal to A2 minus A mean, and so on till delta AN is equal to AN minus A mean. Okay. Delta A calculated above may be positive in certain cases and negative in some other cases. Fine. But absolute error delta A will always be positive. Quite evident because we are using magnitude value, so magnitude of anything will be always positive. Right? Delta I can be positive or negative depending upon either A mean is less than that AI value or greater than AI value. Next thing is the arithmetic mean of all the absolute errors is taken as the final or mean absolute error of the value for the physical quantity A. It is denoted by delta A mean. So what is delta A mean now? Delta A mean is similar as we did for A mean here. In the case of every A1, A2, A3, we will directly use just delta A value. So delta A1 mod of delta A1 plus mod of delta A2 plus mod of delta A3 and so on till mod of delta AN divided by n. We can also write it as summation I is from 1 to n mod of delta AI by n. Okay, so just if you can refer this, you can remember this. So that is the basic crux we are trying to understand this first lecture. Okay. Now, if we do a single measurement, the value we may get is in the range of A mean plus minus delta A. Quite evident. Anything which you will get will always be equal to A mean plus A delta A mean to A minus delta A. So basically A minus delta A mean to A plus delta A. Right? It is also given. This is also written. Okay. This implies that any measurement of the physical quantity A is likely to lie between A mean plus delta A mean and A mean minus delta A. Instead of the absolute error, we often use the relative error or the percentage error. Okay, what is this percentage error? First of all, for calculating percentage error, you should first calculate the relative error. Okay, the relative error is the ratio of the mean absolute error delta A mean to the mean value A mean of the quantity measured. So relative error is equal to delta A mean upon A mean, and hence when the relative error is expressed in percentage, it is called as percentage error. Therefore, percentage error is equal to delta A, which is equal to delta A mean upon A mean into 100%. So just understanding you again. So first of all, what we did was we had these quantities. We had quantities A1, A2, A3. Let's say we have only 4 quantities for now, right? What will be A mean? A mean will be equal to A1 plus A2 plus A3 plus A4 divided by 4. Right? Then next thing will be delta A1, delta A2, delta A3, delta A4. This will be A1 minus this complete value. Let's say write as equation 1. Let me use directly A mean only. Okay, so this will be A mean. Similarly, this will be also A2 minus A mean only. Similarly, A3 will be delta A3 will be A3 minus A mean. A4 will be A4 minus A mean. Okay, please remember in this case scenario, A mean is observed or is been approximated as equal to 2. Okay, After this thing has been done, just find out the value of delta E mean. So this delta E mean will be nothing but equal to delta A1 plus delta A2 plus delta A3 plus delta A4 divided by 4. Next thing will be relative error. So relative error will be equal to delta A min upon A min. And percentage error will be equal to delta A min upon A min into 100. So that is how percentage error is calculated. So this is the complete concept which we understood in the last 10 minutes. Okay. So therefore relative error is nothing but delta A min upon A min, and percentage error is nothing but delta A min upon A min into 100%. Okay. So let me stop the lecture here only. In the next class, I will start with this example. So right now, introduction has been done. SI unit explanation is being done. Measurement of length is done. Measurement of mass is done. Measurement of time is done. Right now, we have a sixth part, that is accuracy, precision of instruments, and errors in measurement. Then we'll go on to significant figures. This is very important concept. And dimension of physical quantities, again important concept. And dimensional formula and dimensional equations, how are the dimensional equation being utilized, what is this dimensional formula, and finally dimensional analysis and its application. And then the complete chapter will be over. Okay, so just stick back. Very easy chapter. We will do it quite clearly. I will try to explain each and everything which I can. So thank you for today.